starting the next session. So, all right, well, the next talk is the systems update, which I've given each year we've had this conference. And so I'll just start that up now. So I don't think I need to give a speaker introduction. All right, so everyone see my screen there all right? Except I'm not actually screen sharing. That would be a no then. And maybe you can see my screen there now. How about that?
Yes, we've got it now.
Great. All right. So this is the systems update for 2022. And as usual, I sort of give a summary of what's been happening at the lower levels of ArduPilot. And there's certainly been a lot happening over the last year. So just a few little stats there at the beginning. 5,000, as of when I made this slide, 5,694 patches have been merged in the year up to the point where I made the slide just a couple of days ago. Over 3,300 PRs. So it's around a 10% increase over the previous year. So we tend to sort of be increasing year over year. About 350,000 lines of code have changed in ArduPilot in the last year, and we had 180 people contributing code in the last year, code and documentation, which is really a great, really great to see so many people contributing to the project. So firmware size has become more of an issue, and a lot of the discussions on our weekly or actually bi-weekly development calls now have been, whether we accept a feature in and the flash cost of the features. So you can see a picture on the top right there showing the state of the build server as of the time that I made this slide, and showing that we were really low on space with many of our builds down to the last few bytes. And so it has actually improved a little bit in the last couple of days. We merged a change here. So if I bring up the build list we've got at the moment, you can see that it's looking a little happier. And we've got just a couple that are low on flash space, but things are considerably happier. And this is just because in the last few days, we've merged a patch that built upon some work that Henry did to disable all but the U-Blocks driver on our really low flash boards. So the boards that were completely running out, the ones that were in this list down to their last few bytes, we've now disabled everything except the U-Blocks driver. The thing that's really allowed us to do that has been the introduction of the custom firmware server, custom.ardupilot.org. So this custom firmware server and really great work that was done by Will Piper for the GSOC project last year, and it's been very popular. So this is, if you haven't seen it before, I think most of the people on this call would have seen the custom build server. Basically, it allows you to go in and select a flight controller and pick the features that you want to include, and then do a build for that particular flight controller. So a bit more about that later in the talk. All right, so back where I was having my slides, great. All right, so ShibiOS update. So we're still using ShibiOS 20.3. We'd just moved to 20.3 in my last system update. We're about due for the next major ShibiOS revision. And so we've already been doing some experiments with the 21.11 version of ShibiOS. And so the plan is that when we've sort of released the final version of 4.2.0, there will be a PR to update us to the 21.11. These are sort of year and month releases. So that's the November 21 release of ShibiOS. And so that's what we'll be targeting for the 4.3.x versions of ArduPilot. It's not a really major change, but there are a few key features that are important for parts of the project. One of them is improved QSPI support, which is really important as we've got new flight controllers coming out that come with QSPI flash. And the main driver behind supporting QSPI flash are really two things. One is some flight controllers rely on it. So there's the SP racing boards that Andy Pipe has been working on, which only have a 128K of flash, and then they have a QSPI flash chip with a lot more flash, hundreds of megabytes of flash space available. And that basically is seen as external flash that can be memory mapped into the address space on the flight controller. To provide that, there are some issues with performance on that, but I think we'll be able to overcome those in the coming months. And it's going to be quite important as we keep adding features and we run out of flash space to have really good support for QSPI flash. And I know that some other vendors are planning to incorporate QSPI flash parts of 100 or 200 megabytes in future versions of their boards. So that's going to be quite important, the improved support for that. A big one is that asserts can be non-fatal. For those who are building their own firmware at the moment, one of the things that we recommend people doing whenever they're making significant system level updates is to do a build with the enable asserts option to configure. And when you do that, then Shibios checks a lot of the APIs. So if you, for example, you make a mistake with locking, or you use the wrong, Shibios class function from interrupt context or from thread context or whatever, there's a whole lot of checks for the validity of the Shibios low-level system calls. And what happens at the moment is when you violate one of those checks, that it will call a system halt, and you'd then be able to attach a debugger and get a backtrace. And that's great if you're doing bench testing, but less useful for a flying vehicle, because halting it will mean that the vehicle falls out of the sky if it's a flying vehicle, or perhaps floats off into the distance if it's a boat or a submarine. So what we'll be able to do in Shibios 21.11 is we'll be able to map these assertions to a non-fatal error, and we'll be able to map them onto our internal error system. And that will mean that they'll be logged in our onboard logs. They'll be able to be transmitted down to the ground station using MAVLink to say you've had an internal error, and we'll be able to examine those at our leisure without it causing a fatal exception. And I think that's going to be really important for catching these types of errors. We have had situations where an assertion has been failing for a considerable period of time in master before somebody does a build with for that particular type of configuration. For example, D-shot or a particular UART configuration before it's noticed. And so this will mean it will be possible for people on their normal development test vehicles that they're doing test flights on to be able to enable the assertions and map them into our internal error system, which should allow us to catch those exceptions a lot more quickly. It will cost us some flash space, so we're yet to decide whether we're going to make that in our default builds, but we certainly should at least make it available in the custom build server and in builds that individual developers do for their for flying on their own aircraft. And then we can decide at a later date whether we're going to enable these types of asserts with our general builds that our end users are going to get. Improved Ethernet support. So Ethernet is going to be, I think, an important part of the 4.3 development series. So we've already got some work being done by Tom and Sid on Ethernet support, and we've already got example flight controllers that have got Ethernet connectors. And so Ethernet's going to be, I think, more important, particularly in larger vehicles. So the improved support for Ethernet in the 21.11 release of ShibiOS is going to be very welcome. Finally, there's a completely new virtual timer implementation. And this was largely sparked by the discussions that we had with the ShibiOS core developers about some of the issues we had with lockups in the timers. And that's been an ongoing problem with the older release of ShibiOS that we've had. The 68 millisecond delays, for example, on the Maytech H743, and more recently where we had some watchdogs, which we spent a lot of time investigating. The core issue behind that is that the virtual timer implementation, which is the part of ShibiOS that schedules threads. So when a thread says, I want a delay for 3 milliseconds, for example, that it places that thread into a linked list of threads that are waiting on an event of some sort, on a completion of that wait, and the process of placing it into the queue relies on a certain piece of code running within a limited amount of time, and that's called the scheduling delta, which we've got set to a fairly conservative value of 10 microseconds in ArduPilot. The new implementation doesn't depend on that, which means that those types of problems where we had flash causing very long delays and causing a watchdog should be completely a thing of the past with the new virtual timer. But so in the meantime, we've just had workarounds in our current version of ShibiOS. So quite recently, the latest beta of Plane and the upcoming beta of Copter, we've switched to disabling interrupts during flash operations to make that time more predictable in the virtual timers. All right, so that's sort of it on what's happening with the core ShibiOS version. So I expect that in the next month or so that we'll have that PR and start switching to the 21.11 version of ShibiOS. Feel free to ask questions as we're going along, by the way. Okay, so some of the highlights of what's been happening in ArduPilot over the last year. And these are in no particular order and or no particular level of priority. And it's just some of the ones that I think are really the high points. There's been, as I said, 5,500 or more patches gone in. So there's been an awful lot of changes. But I think some are worth mentioning as really key changes that have happened in the last year. The first is support for CanFD. And so that effort was led by Sid, and really nice piece of work. Hang on a second while I just sort out an audio problem here. All right, that should fix that up. Okay, so so really nice piece of work supporting CanFD. So this is part of the effort that moving to DroneCan. And so we're basically adding support for higher bitrate, what's called bitrate switching with CanFD. That'll mean that at the moment, all of our CAN packets are going at 1 megabit. And where we're using what's called BXCAN or conventional CAN packets. With CanFD, the way it works is that the framing for the CAN packets remains at 1 megabit, but we're able to send the data at a higher bit rate. And the likely bit rates that we're going to allow for is 5 megabit and 8 megabit as the most common ones. But key to that is the some work that is upcoming that I think Sid will be explaining in more detail, which is to be able to negotiate what bit rates are available across all of the peripherals and the flight controllers that are connected onto the CAN bus. So we've got a negotiation system that will make that possible. And I'm sorry, I've got another little audio problem here I just need to fix up. I kept getting an echo from my other computer. All right, that's gone now, great. So hearing myself echoed with a couple of second delay was slightly annoying. Okay, so CanFD has gone into master now. It's not in the 4.2 betas, but it is in master. So it is actually possible to configure now ArduPilot with CanFD, and you can select the bit rate. What hasn't gone in yet is the support for negotiating the bit rate between the different components. And that's really an important part of the support before we can really go live and start recommending that people start using CanFD. And so there'll be more about that in Sid's talk. QSPI Flash support, so that's the basic support for QSPI Flash has gone in, so we can support things like the SP Racer board. As I mentioned before, this is really important for expanding the amount of flash space, the amount of code that we'll be able to have in ArduPilot. And it is going to be an enormous expansion going up from, typical flight controllers, either 1 or 2 megabytes of flash, up to hundreds of megabytes of flash available in some flight controllers. Parameters in Lua scripts, I think, was a really nice step forward. That makes it much easier for users to configure Lua scripts, and allows us Lua scripts to move closer to being first-class citizens in the world of ArduPilot. Adding support for real applications and extensions of the ArduPilot capabilities from Lua. So being able to create custom parameters, both in terms of parameters that are completely new parameter spaces, new name, with completely new naming prefixes, and also extending existing parameter trees, which we've already got some examples of. So in the last year, we've introduced double precision navigation and estimation. That was a fairly major change which we applied to both EKF2 and EKF3. And this is part of an effort that I called Extreme ArduPilot to support really long range navigation. So we've demonstrated, at least in simulation, that ArduPilot is able to fly right around the world, so circumnavigate the Earth in an aircraft. So I did that with a large fast aircraft in X-plane, and the EKF was able to remain stable over the entire flight. We did have a limitation of 1,000 kilometers previously with our EKFs, and although that was the hard limit, we actually had estimation errors start to come in at much shorter ranges, and our navigation code, the copter control code, for example, started getting oscillations at distances of the order of a few hundred kilometers. So with the double precision estimation that we now support on suitable processors, so that's on the F765 and above, and the H7 processors, which many, if not most people are now running. We now can support essentially unlimited distances. We still do have a constraint if you're flying very close to the poles. So if you were trying to orbit, within hundreds of meters of the North or South Pole, then our estimation system will still have significant issues. And so that's something that requires another level of rework that has been discussed by Paul Riseborough and myself, but hasn't been implemented yet. We have had people flying down in Antarctica and up in the Arctic area, but I don't think they're doing much auto navigation right near the poles, because the state estimation, at least using the EKFs, starts to get very unhappy if you're very, very close to the poles. Similarly, there's a little bit of a problem with our magnetometer support close to the magnetic poles. So the way we do our interpolation on our declination and inclination tables, that interpolation is too coarse-grained near to the magnetic poles. So if you were flying very close to magnetic poles and you were using a compass, you'd get significant issues. That can be solved by using the dual GPS moving baseline yaw, but it would be nice to have better support for flying with a compass close to the magnetic poles. It's just a matter of us changing the way we do the interpolation to better support that. Another major change was the ESP32 HAL. So we now have, it's the first time we've had a new HAL in quite a while. supporting the little ESP2 boards, which brings a really low cost solution. And there'll be more discussions of that later on with Nick's talk with Buzz. So many thanks to the enormous effort put in by Nick and Buzz to support the ESP32. It's been a really nice piece of work. We've had the switch over to DroneCAN. So this is away from, it's partly just a renaming, but it also sets the scene for us doing some fairly major evolution of our CAN protocols. And that's really gone rather smoothly. Some of you may not have seen an announcement as well by the UAV CAN project. Pavel announced that they've also renamed. So UAV CAN now, the name UAV CAN is no longer associated with an ongoing project of any sort. So, so DroneCAN is the successor to the original UAV CAN protocol, and what Pavel and the UAV CAN dev team was calling UAV CAN v1 is now called CYPHAL, C-Y-P-H-A-L, I think it is. The name UAV CAN still, of course, appears in a fair bit of documentation and on labels on devices and things, but over time, I hope that people will start using the name DroneCAN. And we've also started some significant development within DroneCAN. So particularly around the GUI tool, it's had a lot of enhancements in the last few months, and new messages coming in. And the new node capabilities to negotiate the capabilities of all of the devices on the bus. That's in prototype at the moment, being worked on by Sid and myself. And that's going to set the scene for us doing a fairly major evolution of the messages, bringing hopefully a lot more sanity to the message structure. Our custom build server that I've mentioned before, really big development. CAN over MAVLink. So this is part of the DroneCAN project. We now support forwarding CAN, both CAN-FD and the older BX-CAN messages over MAVLink. And I'll be giving a demonstration of that later on in this talk, because I think it's a really useful diagnostic tool. MicroSD formatting over MAVLink. This is something people have been asking for quite a while. If you've got a flight controller deeply embedded in a vehicle, then it's very useful to be able to format the microSD card in case it's corrupted or you just want to wipe it out and start again without having to pull it out of the vehicle and pop it into a separate laptop and format it. So we now support a command to format the SD card over MAVLink. That only works for SDMMC style SD cards at the moment. So they're the ones that are doing SD cards over SPI, which is used particularly on some of the F4 and F7 and smaller boards. We don't as yet support formatting those over MAVLink, though I would hope that we add that in the 4.3 timeframe. Finally, the log rate max parameters. I thought I'd mention those because I think there's a number of partners who might benefit from those. If you're doing very, very long flights, and some people are, like I saw recently, an ArduPilot quad plane, the electric quad plane doing a 6-hour flight, which is quite remarkable. And some people do even longer flights. Tom's been talking about flights that go for more than 24 hours. You've now got the ability to rate limit the log messages, and which is very, very useful. And you can separately rate limit the log messages going to your SD card and going out across your link to your companion computer. And that's really great for keeping the bandwidth that you're using up going to the companion computer down to a reasonable level, but also just constraining the how big your logs get when you've got really, really long flights. Something that I've been meaning to do is write an example Lua script that adjusts those rate max parameters based on the stage of flight you're in. For example, in a quad plane, you might like to have unlimited rate of your messages during the takeoff and landing and during the approach. But during the cruise portions of flight where you're doing a long auto mission, you might like to drop back the maximum rate limit. And it does support changing that dynamically. So it'd be quite possible to have a very simple Lua script that just looks at the stage of flight and adjusts those rates. And that would allow you to have the highly detailed logging during the really critical portions of the flight when, for example, during the takeoff and the landing. But during the long and hopefully boring parts of the flight, from the flight controller's point of view, reduce the rate that it's logging messages down considerably so that you don't get quite so enormous logs. And so I'll put together an example Lua script that does that hopefully sometime soon. All right, so there's sort of main system highlights over the last year, now move on to a little bit on some of the CAN changes. So as I mentioned, so CAN FD support has been started, and more on that in Sid's talk. We've started on the DroneCAN node capabilities message, which is the basis for us negotiating between all the devices on the bus as to what each of their capabilities are. So we use the minimum, we work out the minimum level that all of the different nodes on the bus support. So we make sure that when we move to a new message that replaces an old message, that all the devices that are consuming that message are happy. CAN translation is now possible in AP-perif. This was a really interesting capability added by Tom. So it's now possible to have, for example, a G4 peripheral, which has 2 CAN ports, and to have one of those CAN ports talking drone CAN to the flight controller, and another port talking a completely different CAN protocol. It might be, for example, Piccolo CAN, or in the case of Tom, he had the MPPT CAN driver, the maximum power point tracker for solar cell management. And being able to do that translation really solves one of the core problems that CAN has, that you can only have one extended CAN protocol live on the bus at any one time. And so this allows you to use a translation node to translate from one extended CAN protocol to another. Now, something that I would like to add into 4.3 is, as I mentioned specifically, that you can only have one extended CAN protocol. You can, in theory, with a CAN bus, have one non-extended CAN protocol and one extended CAN protocol. So you could, for example, have a CAN LiDAR that uses a custom CAN, 11-bit addressing CAN protocol at the same time as having drone CAN on the same network. And so what I'd like to do is add a parameter for selecting one additional non-extended protocol to run in parallel with your main drone CAN protocol. And that would make things a lot easier. Cabling wise, you'd be able to connect up, for example, a CAN LiDAR or CAN radar, and put it into the same CAN bus as your existing drone CAN network. And that would be a lot easier on the cabling to be able to mix the two on the same bus. And it's just a matter of registering that additional protocol and making sure that all the non-extended packets go to that protocol handler and all the extended packets go to the drone CAN packet handler. So we now have 3 different types of CAN servos that are available, which is really great. I've been wanting it for fixed wing for a long time to have CAN servos to be, get more adoption of those. So we have a new CAN servo from Hitech. I actually got one here on my desk somewhere that I was just sent recently. Now I can't see it under the pile. And we've got the CAN servos from Zeus, and of course the Piccolo CAN servos from Karawong. So users now have a choice of CAN servos. And this is, getting us down towards the point of having all CAN actuators, so CAN ESCs and all CAN servos, which really give you a lot of advantages as far as having feedback available from all your actuators. So the next steps in CAN development, the complete the addition of node capabilities, and for the negotiation of the capabilities of each of the nodes on the bus. We want to build much cleaner drone CAN DSDL backwards compatible with existing nodes using the node capabilities to maintain the backwards compatibility. That includes the CAN-FD speed negotiation, and there'll be a lot more details of this, and I think some demonstrations in Sid's presentation. All right, so Lua has had a lot of work done over the last year, and so it's really been rapidly maturing, and the scope of what people are using Lua for is really expanding very rapidly. So I wanted to point out some of the highlights that we've had in the last year in the world of Lua. I mentioned earlier the parameters in Lua scripts, and I've got a little example of that down here in the bottom right corner. So this is from an example where we're extending the follow capabilities of a copter. So we've got an existing parameter tree, which is prefixed by FOLL_, and we can now add a new parameter table with that same prefix, and then we can add 2 new parameters. So we end up with FOLL orb radius and FOLL orb time. They're the orbit radius and orbit time, and that allows you to set up follow with orbiting around the target point rather than just in a fixed location about the target point. And it's an absolutely trivial Lua script to add support for orbit, and it's a great example of the way we can extend existing capabilities of ArduPilot with a Lua script without any changes at all in the C++ code. And being able to then add the parameters into the existing parameter space, I think is really powerful. We now support logging of Lua scripts for better diagnostics. I'm finding that really useful when people are using a Lua script, and I'm not sure exactly what version of the Lua script they've got loaded. We now log the exact Lua script, the contents of the Lua script inside our onboard logs, and that's really powerful for being able to work out when there's a bug. For example, in the log, we might get there was an exception in a Lua script at a particular line number, but we don't know what that line number corresponds to based on the version of their script. And so now we've got the full Lua script that was being used during the flight available, and we can go and look at exactly what was being used and what needs to be fixed. So there's been some really nice work by Henry on expanding our applets. This time last year, we had just started the applets directory, and there was a single just sort of placeholder example applet. And now we've got a lot more applets. And so the ones that have had the most development, the fixed wing aerobatic scripts from Henry is really quite amazing, the work he's done there, where he's able to have switch positions to do, for example, a loop or a rolling circle or a knife edge or inverted flight, etc. And being able to select those on switches. All of that was done using Lua scripts and the scripting that Henry did, where it's one of the first examples where we've got multiple Lua scripts cooperating with each other. So he's got a core Lua script that's handling the switching, and then he's got additional scripts that provide the functionality of each of those. And so we have a set of Lua scripts that get loaded, and those are collaborating with each other, which is a really nice thing to see. And so that's one of the most complex sets of scripts that we've got at the moment. Mission selection, where you can use a switch to switch between different missions. So you might have multiple missions and you want to be able to quickly switch between them. So there's a nice little mission selection applet. Smart audio control applets for controlling power levels on your video, your FPV video system. Forward flight motor shutdown for turning off different motors in forward flight, useful in quad planes where you only want to have a subset of your motors running in forward flight, and the on-VIF camera control, and that's for controlling the pan tilt zoom on-VIF cameras. So really nice to get those done as little applets with documentation. The key difference between an applet and example script in the Lua scripting for ArduPilot is that the applets come with documentation how to run them, whereas the example scripts just tend to have a few comments on the top of the file. And Henry has been our gatekeeper in ensuring that we get decent documentation on the applets and get them documented in the wiki. So thank you very much, Henry, for that work. I've mentioned the custom build server before, and it's certainly been a really, really useful addition, and it's basically been a key enabler for us to start moving some of the lesser used features of ArduPilot to not be built in by default, which is essential as we just keep running out of flash space. We're basically maxing out the available flash space on many of our boards, particularly the boards that only have 1 megabyte of flash. But we're down to, you know, under 200 kilobytes of flash left, even on some of our 2 megabyte boards. So it's going to become more and more important as we keep adding more features. We typically add about 5 to 10 kilobytes of flash space a week to ArduPilot of sort of new features. And so being able to move those off to only being, you know, the lesser used features that are only enabled on the custom build server is really important. It also allows us to move the really rare sort of one-off flight controllers to be only built on the custom build server. So particularly for boards like this is a Nucleo board, so it's a prototyping board and not something you would generally fly with, although people have flown with that sort of board. I've seen pictures, and it's not necessarily a good idea, but it has happened. So those types of prototyping boards, we've shifted those across so that they don't get built in our standard builds. And instead, you can go to the custom build server and ask for a build for one of those boards. And you say, you know, what type of vehicle you want and the board and all of the features you want, and it'll build you a firmware. So So it's been a very useful project, but there are some really key missing features we don't have at the moment, which we're hoping to fill those gaps this year, either as part of a GSOC project or just as general development. Really, really important, we need to support beta and stable branches so that people can do custom builds on our betas and stable releases. And that's going to become, you know, more and more important as we move features out of being in our standard builds and move them only to be on the custom build server. So hopefully we'll get that in fairly soon. Support for developer feature branches, I think, is similarly very important, particularly when there's long-term development happening of a feature. And you want to get everyone in the community, you know, your set of testers that you might gather together on discuss.ardupilot.org, and you want to be able to easily provide a build for any flight controller of that feature. So we really need to be able to, on the custom build server, select those developer feature branches and have a way to build those. Finally, we really need some better dependency checking. It's all too often that people find that they choose a set of features that don't go well together, and they end up with a failed build on the custom build server. So we really need to have better way of checking that you're enabling a sensible set of features. Or really, the important thing is if you enable a particular feature, that all of the other parts of the code that are dependencies of that feature get automatically enabled as well. All right, so most of the rest of my talk is on diagnostics and error handling, and I decided to focus on that in this talk because I think it's something that a lot of developers are not aware of, some of the features we've got for diagnosing errors, and that it's also very useful for partners who are trying to diagnose problems with their users' systems. So what I'm going to be doing is demonstrating how to use some of the key diagnostic systems that we have. And many of these diagnostic systems are new in 4.2. Some of them were available in a prototype form in 4.1, but most of them are completely new in the 4.2 releases. So I'll be talking about using the crash catcher system for handling catching hard faults, the way we log system files, how we log system storage, looking at stack usage, improvements to our internal error handling system, and finally I'll give a demonstration of CAN over MAVLink. So I'm going to start with a diagnostics example, and this is from a bug that we had that was fixed just a couple of weeks ago. And so what I'm going to do is stop the full screen here. And instead, what I'm going to show you is I've got a Cube Orange flight controller here, and this is running a version of the plain 4.2 firmware from just before this bug fix went in. And I wanted to show you how you can do some interesting diagnostics with this board. So what I'm going to do is connect to this board. So now connected into that board. And I'll just raise the font size a little bit here. So is that big enough for everyone to see what's happening there? Go a bit bigger?
Yeah, that's good.
That's good? Okay. All right. So now I'll just demonstrate this particular bug, and then I'll show how you can use some of our new diagnostic tools to diagnose the what's causing this bug and fix it. Now, this particular bug was one that if you set the airspeed type, it doesn't stick. So I'm going to go and change this airspeed type, and I'm just going to, pick a random number. I'm going to set it to say 5, right? And it really doesn't matter what I've set it to. And then I'm going to param fetch the airspeed type, and we can see that it is indeed set to 5. All right, so this is all quite normal so far. We've just set a parameter to a particular value. And what I'm going to do is I'm going to reboot the flight controller. Okay, and there it is rebooted. Great. And now I'm going to fetch that parameter again. And it's back to 0. Right, so this was one that I actually hit myself on one of my own quad planes. And very frustrating. When you set a parameter, it does set for that session, but then as soon as you reboot, the parameter disappears. And this type of bug can be very difficult and rather frustrating to track down. Now, if you can't find the bug immediately and you can't easily reproduce it, then what we would have done before is we would have, for example, attached a debug adapter to the board. And if you've got the appropriate cabling and you've got the right sort of board that's got debug capabilities. But what I'm going to show you is a method where we can diagnose this without having to get debug on the board. And so the technique uses the fact that within our system storage, so if I show here, these are our sys files, which we introduced in last year in 4.1, the use of system files you can fetch via FTP, but we've greatly expanded the number of system files. And one of the system files we've added is storage.bin. Now, storage.bin is a complete copy of the system storage on the board. So in this particular case on this Cube Orange, that's the FRAM chip, the 32 kilobyte FRAM chip. And that's why this file is 32 kilobytes long. On a board like, say, a Maytech H743, it would instead be, and I just need to somehow get rid of those silly notifications there. Well, I'll ignore those for now. Okay, so on something like a Maytech A743, it would be the 32 kilobytes of data that's represented in the flash sectors that particular board uses for its storage. But the reason this is important is the existence of this file, being able to download this virtual file from sys, that allows us to transfer the bug if the bug is related in any way to the to all the parameter sets. We can transfer that across to the computer and put it into CITL. So what I've done is I've downloaded that sysstorage.bin, and so there I have that file, that 32 kilobyte file now on my local system. Okay, and so that's a complete copy of what was in what is currently in the FRAM on this Cube Orange. All right, so what I'm going to do now is I'll just go make a nice big font there too. And I'm going to copy, see what directory I was in my conferences APM 22 directory. So I'm going to copy from conferences APM 2022, that storage.bin file, and I'm going to copy it over the file eprom.bin. So in CITL, we use a file called eprom.bin to emulate the storage on a flight controller, and it's the same size, 32 kilobytes. So I've just copied that file that I've downloaded from a real flight controller, and I've copied it over the eprom.bin file that I'm going to use in CITL. All right, which means that I'm going to be initializing CITL with exactly the same contents for all of the parameters, the rally points, the mission, the fence, etc. All of that data is going to be exactly replicated from the real flight controller into the simulator. Okay, so now what I'm going to do is Tools, Auto Test, Sim Vehicle, and I'm going to start up our normal simulator here. All right, so that will fire up the simulator. Wait for that to start up. Okay, so there we have the simulator running, right? And let's first of all check. So we've got a GDB session here. So we've got a debugger running. And the first thing I'm going to check is, have we replicated the bug? So we've now, does the bug actually transfer across? And the trick, of course, is you want to run exactly the same version of the code in CITL that was running on the flight controller where you had the bug. So what I'm going to do is start by param fetch airspeed type, and it's currently set to 0. Now I am going to go and set it in CITL, and I'm going to set it to, another value like 10. And check that it is set, and it is indeed set to 10. And now I'm going to reboot CITL. So it's now restarted, and I fetch it, and it's now 0. So we have now replicated the bug. We've successfully transferred the bug from a real flight controller into the simulator. And I'll be showing in a minute how you can transfer this from a user's log. You don't actually have to have the flight controller locally. You can actually get that storage.bin out of the logs from a user. All right, so we've now replicated the bug. So I thought I'd do the next step, which is to actually find the bug. All right, so what we're going to do is I'll just break in the debugger here, and I'm going to have a look at that variable, plane.airspeed. I'm sorry?
Can you make the debugger any bigger?
I'm not sure I can. It's already on huge. Sorry. I could, however, attach it in a different way. If it's really is hard to read, what I'll do is I'll start it again, but I'll start it without the -G there, and then I'll attach it in another window instead. And that will allow me to have better control over the font. So that should be a bit clearer. So GDB -P PID of, all right, and okay, and all right, so that's actually, I'll just, yeah, unfortunately my terminal has stuffed up. And let me just reset that terminal and attach again. All right. Okay. So what I'm going to do is now P of plane.airspeed.param 0.type._value. Right now, that's I just happen to know where that variable is stored. Otherwise, you can look it up in the code. So that's the actual value of that airspeed type parameter. All right, and so I'm now going to add in a watch point on that variable. So that will show me when that parameter changes, right? So when that variable changes. And so now what I'm going to do is I'll just, continue in there. And here's where I am running that. And I'm going to go and param set airspeed type. And I'll set that to say 11. Right, and in my debugger, it's now showing where we're setting it. So it's calling the set on the variable. So I'll just let that continue. And we can see the old value was 0 and the new value is now 11. So we'll just let that continue like that. And so now what we're going to do is we're going to restart the program and watch when that changes again. So I'm going to go there and I'm going to go R to rerun. Right, so R to run, starting it from the beginning. And it, first of all, it's going to show us each of the times that this value changes. So it's starting at 0 first from the initial 0 memory, and then it's changing to value 2. And if we look at the backtrace, we can see where it's changing it to 2. That's just the setup object defaults, because the default in CITL is 2. So that's not really interesting, right? So let's continue and see when it next changes. And when the restart with the attach, darn it, I have to do it with the -G because it's not restarting with the attachment. I'm sorry, you'll have to put up with the small font for me to demonstrate this one. So apologies about that, but I'll run through it fairly quickly, and then you can always squint at the video later. All right, so what I'm going to do is go and param set airspeed type to 12, and then I'm going to put a watch on plane.airspeed.param 0.type._value, so I can see all of the, and we can have a look at its current value. It's currently 12, and then I'm going to go and ask it to restart. And we see it first of all changing to 2 with that default. And then we're going to see it changing to value 12, which is the value that we do want. So that's where, if we look at the backtrace, it's getting that value 12 from where it's doing load all. So that's our parameter load all where we're starting up. So far, so good. This has got the correct value at the moment. But let's now continue and see what happens. And there we see it changing from a value of 12 now to a value of 0. So this is the point where we're getting the value being reset. And if we look at the backtrace here, we can see exactly where that is happening. So if we go up to there, then we can see there's the code. So this is the line of code, and we can see that the issue is in our convert class code, which is doing the parameter conversion. And so that's the bug. And so there was a patch now to fix that so that it doesn't always do the parameter conversion. What it was doing was getting the value from the old 4.1 area before we converted the airspeed class. But the details of the actual bug itself isn't what I'm really wanting to show today. I just wanted to show the technique of transferring a problem from a real flight controller to a simulated flight controller into CITL. And that's a very powerful technique to be able to move across the entirety of the storage from a real flight controller into a simulated flight controller. All right, any questions about that?
Tridge, I got a quick question. I don't fully understand why do you need to transfer the EEPROM from the flight controller onto the sim? Because the bug is in the firmware. So surely, take this example that you've just gone through, couldn't we have just run CITL to replicate the problem because we knew that there was a problem with that parameter set?
If we knew what the problem was, yes. But we didn't know that it was to do with the parameter conversion. We didn't know that the reason this bug existed was that this particular flight controller had been shifted from one aircraft to the other, and it used to be running the particular flight controller had gone through a history. Nobody noticed this for months, right? Because the flight controller had to go through a particular history. So the flight controller was originally installed on an aircraft with an airspeed sensor. And then it was moved to an aircraft without an airspeed sensor, which means the parameter was changed from being a non-zero value back to a zero value. Now that wrote that zero value into the EEPROM using the old parameter tree. And then it was moved to another aircraft where I then wanted to enable an airspeed sensor on that new aircraft. And I found that the parameter kept getting reset. But I didn't know what the bug was. I didn't know that it was because this wasn't happening on other aircraft. Other people found that they could set airspeed type all they liked and it worked. And in fact, we've even got, we had auto tests and we tested at the time, we added the class conversion code, etc. So it was the particular history that was embedded in what was stored in this particular storage.bin, the FRAM, right, is what we're trying to capture. And it's obvious now that we can see the bug, what the actual thing was, and it is because of that history. It wasn't obvious at the time that the bug actually occurred. And so this allowed me to basically move it across into an environment where I've got a much more powerful debug system, where I've got, watch points and a full, desktop debug system, a much easier environment to work with. Does that make sense?
That does, yeah. That's great. Thank you.
Yep. All right. Any more questions about that system of sort of moving things across from real flight controllers to simulator?
Yeah, I have a question. So it's transferring all the storage of whatever's in the flash or the FRAM on this particular board. So is that the same? Like, how does the simulator adapt to different boards? Are there any like format differences between boards with different sizes of FRAM or anything? Like
so there are. So there are some boards, for example, if you were doing this from say a Kakut F4, which has a storage size of 15360, oddly enough, that's a particular number that works in with the way our flash storage system works on those boards. You would need to run CITL with that same layout. Because of the way our storage manager works, we have a different layout of storage in different boards. Now, so it just so happens that, our more sort of premium boards, the larger boards that are using FRAM, so like the Cube Orange and CUAV, X7 and Durandal and Pixhawks and all those boards, they all use this same 32 kilobyte size that CITL uses, which means it's very, very easy. But if you are on something like a Kakut F4 or an Omnibus F4 Pro or similar, you would need to change one line in CITL to make CITL use that same storage size, 15360. And I can go off and show you where that line is if you like. But if you do need to do that, it is a one-line change in CITL to make those sizes match. There's also things about parameters. There's certain parameters that won't come across. There are parameters that don't exist in CITL that exist on real hardware. For example, there's a parameter that controls whether we do 3.3 volt to 5 volt level shifting on the outputs of pins, right? That's a very hardware specific parameter that's only on certain flight controllers and isn't in our simulator. Now, those parameters just won't be shown in CITL. Because of the way we do our keying of parameters in our storage, the keys are unique, even if it's on, as long as it's the same vehicle type, the keys are unique. So you don't end up getting collisions between the CITL parameters and the hardware parameters. So it actually does work really quite well. You will find, for example, all of your mission is transferred, your rally points are transferred, your fence points are transferred. All of those things are transferred across. And all of your key parameters, your flight control parameters are transferred across. So it's not so much for actually going and then flying it in CITL, because you know your tuning and the mapping of your servos and things is likely to be different in CITL than it is on the real vehicle. It's really for this sort of low-level debugging where you're trying to find, you know, why particular behavior is misbehaving, and you want to replicate as closely as possible the environment of the real hardware within the simulation environment.
I feel like the answer to this question is no. Why would you ever do that? But can you upload the storage.bin?
Not at the moment. I have considered making it writable. We do make some of our system files and our sort of virtual file system files writable. For example, our mission file is writable. You can upload a mission using FTP as well as download, and as our geofence ones are uploadable and downloadable. So there's some, and our same with our parameters. You can upload parameters with FTP as the parameter file and download. I haven't done it for the storage. We could. There would be some synchronization and locking issues that would make that tricky, but it would be something we could add if there's a need for it. And one thing that it could be used for is to clone a flight controller. So you want to take everything about all the storage on a flight controller, download it, then upload it to another one, and then reboot, and it will then be identical to the first one. That might be useful.
That's what I was thinking. Like, obviously, you can duplicate the parameters, but you could sort of make it.
That's right. There's more than just the parameters. You know, if you want, there are other storage areas you might want to replicate. And so, yes, it is something that we could add. We don't have it at the moment, but it's certainly something that wouldn't be particularly difficult to add. It would mostly just need to, when it starts the upload, it would have to lock it so you don't get erase conditions, and then upload it all, then wait for it to be flushed, and then you'd need to reboot to actually get for it to take effect. I don't think we'd want to update while flying, for example, your storage.bin. That could get, you know, some very nasty race conditions in that. You'd want to lock it down and then force require that the user reboot for it to take effect.
And sorry, I'm monopolizing the floor.
Please.
You mentioned it's in the log, and is that also included if you're streaming the logs?
Yes, it is, and I'll be demonstrating that in just a second, the way you can get some of these things out of log files. Now, that is only in 4.2. In fact, this whole storage.bin is only a 4.2 feature, but yes, for 4.2, you can actually get the storage.bin off the flight logs that your users send you, or flight logs off your own vehicle. And that's very, very powerful. It means that if they report an issue, and if you suspect it's something to do with a corruption in their storage, a parameter corruption, history of it, parameter conversion, you want their exact mission, their exact rally points. For example, if they didn't, you want to get all of the rally points with exactly the format that it had and all of the details, then using their storage.bin and transferring into CITL is a very powerful way to do that, to make sure that there is really no difference at all, because it's an exact image of what was on that board. All right.
One question. Right, sure. You can use the storage.backs, like that string.backs, right, in previous firmwares to do the same sort of thing, but you have to detective hunt for the right one.
That's right. So there is on some, not on all boards, but on some boards, if you've got an SD card mounted, it will actually back up your FRAM onto the SD card at each boot, and we keep a cycle of those. That is another way to get this storage file, and you can use that similarly to transfer that into CITL. So that works with 4.1. It's just a new thing that we actually have it in flight logs and being able to download it live using the sys file system. All right, any more questions there before we move on? Okay, so I'll just pop back to my slides here. And so what I've got next, the next demo is crashdump.bin. And now this is, so is it going, no, that's great, it doesn't go back to the start. So crashdump.bin, this is a fantastic piece of work by Sid. And so thank you, Sid, for the huge effort that he put into this. So crashdump.bin is storing the information needed by a debugger to get a full backtrace and inspect variables and look at the state of the autopilot, and make that information available via both the sys file system and in a log file. Now, where this is useful is if we've got a bug that is causing for example, a hard fault. Say, for example, we had a stuck overflow, or we had an error where we're dereferencing a null pointer, or we've got, similarly, all sorts of other bugs, all sorts of bugs that we could have in our Jupyter, particularly during the development phase. And when we get those sorts of bugs, being able to actually get a full backtrace and attach a debugger to the state of the vehicle is incredibly powerful. So what I'm going to do in this demo is I've got, in this case, I've picked on a CUAV X7 Pro. So I've got that, and I'm going to attach that to USB cable and show you what can be done with this. So people still seeing the screen okay? Let's attach there.
Yep, looks good to me.
Good, okay. Always got to get some audio feedback, make sure that I haven't, for example, lost network link and I'm just talking to myself. Okay, so what we've got here is I've just connected to this CUAV X7 Pro, and what I'm going to do is use one of the abilities in MAVProxy to deliberately trigger a bug. Right, so we're going to trigger a hard fault on this board. Now, I could have just picked, a previous bug that we've fixed, but it's also quite nice to be able to test this capability. So we've got this command in MAVProxy called hard fault autopilot. Okay, now if you run that, it says invalid hard fault command. And that's because we don't want to, through tab completion, accidentally run this sort of thing within flight, because these commands are active whether you're flying or not. So you've got to give it a string at the end there, which needs to say, I really mean it. And you really, really want to trigger a hard fault on this board, right? So that you don't accidentally, type that in when you're flying your vehicle and regret, that tab completion. So I'm going to trigger that hard fault on this board. And what it's going to do is cause this board to watchdog and reboot. All right, so this is the dreaded watchdog, and it should come back. There it is, booting up again, and there's our watchdog. Now, this is not an all zeros watchdog. This is a hard fault, so it's got all of these hard fault registers. Now, in the past, in 4.1 and 4.0, we just had to try to read the tea leaves from these registers. Right, and that's really all we had, and we would then try to work out, the cause of this hard fault just in those registers, and that was really difficult, very, very difficult task. So what I'm going to show you now is what Sid has developed to allow us to get a lot more information. So if I do FTP list at sys, then what you'll notice is that this file crash-dump.bin no longer has 0 size, right? It normally is a 0 size virtual file. And this is recorded inside our hard fault handler, and it's an image of the stack and memory at the time of our main threads at the time of the hard fault. And it's done in a format that can be accepted by the GDB debugger. All right, so what I'm going to do is download that. Now, that file actually does persist. So you can see one of the things we've often said in the past, don't reboot. We want to have a look at the board and see what's happened. We can actually reboot this. So I'll go and reboot the board, and you don't lose that. It'll no longer be saying watchdog, right? Because the watchdog messages only come up on the ground station at the time when it's booting directly from a watchdog. So we're no longer getting those watchdog messages, but this crash-dump.bin has persisted, and it's actually stored in Flash. What it uses, it takes advantage of the fact that we haven't filled Flash on this board yet, right? We've got some spare space in the top of Flash, and it saves the crash dump into that spare space. Now that means it's lost if you flash a new firmware, because when you flash a firmware, it erases all of Flash, right? But as long as you don't flash a new firmware, this file is still there. So what I'm going to do is, so I'm going to download it, list at sys, and I'm going to ftp get at sys/crashdump.bin, and I'm going to download it as cd1.bin. And the reason I'm calling it CD1 is I'm going to have a CD2 in a minute, where I'm going to show you how to get this same file from a flight log. All right, so we're going to get it first of all. So we've now written this file, which is a 206 kilobyte file, cd1.bin, and fetched in just, a fraction of a second. Okay, so we've now got that log file, and so there's our cd1.bin. Great. So what do we do with that file? Okay, so now we want to find out what was happening in the flight controller at the time that hard fault happened. All right, so what I need to do is, first of all, switch across to the branch that this was running. Now, this was actually running the Copter 4.2 branch. All right, so, and I'm going to back up in conferences APM 2022. I've got this cd1.bin, and just for simplicity, I'll just copy that to the current directory to make the command lines a little bit easier. So cd1.bin is sitting there. So what we do is we run this little script, tools debug gdb crash dump, right? Which is a little helper script that makes it possible to use these crash dumps. And if you just run it, it gives you a little bit of help. And you need to give it the ELF file, which in this case is going to be the arducopter file, and then the crash dump itself. So that's build CUAV X7 bin arducopter. That's the ELF file, and cd1.bin is our crash dump file. So what this script is going to do is attach the GDB debugger ARM9EA by GDB to this ELF binary with this crash dump file for its memory image. All right, so there we are, and it's now processing that. And we're now in there. So we can now do things like info threads, what threads we're running. All right, these were all the threads that were running at the time and what state they were in. There it all is. Now I can actually get a backtrace, and there's a backtrace showing exactly what was happening at the time of the crash, at the time that it had the hard fault. And we can see in this particular case, we were calling the update receive function to receive a MAVLink packet. Then we handle the handle command long, because the force a crash hard fault is a command long in ArduPilot. And then there's the handle pre-flight reboot function, which is the one that actually handles that particular packet, because it's a pre-flight reboot packet with some magic parameters that triggers the hard fault. So we now know that the hard fault happened in that set of code. And so that's much, much nicer to work with than working with just those raw register values. And it allows us to really see what was going on when that fault happened. So very, very powerful. Now, in this particular case, this firmware, this build firmware is a production beta firmware. It's not it's one of our beta firmwares. It's not built with debug. So when I do this backtrace, if I go up, it doesn't show me all the local variables on the stack and that sort of thing, because I didn't build with debug symbols. But even without the debug symbols, I can get the names of the functions. But if this firmware had been built with full debug, then I would in fact get a whole lot. I could inspect all the variables and have a look inside the data structures and that sort of thing. So it's a very, very powerful technique for transferring from a a crash dump from a bug that we've got in ArduPilot and attaching a debugger to that on the after the flight, after the problem has happened. So any questions about that? No? Okay. Well, related to this is the next one is how you get these types of things out of a log file. All right, so I'm going to go back to where I was on this board. So this is again the same CUAV X7 board that I had before. But what I'm going to do now is I'm going to I'm going to load that just so I've got GPS lock, which makes processing logs faster for an odd quirk of MAVExplorer. So what I'm going to do is I'm going to arm this vehicle, and every time we arm the vehicle, we save a certain set of files to the onboard log. And that includes the crash dump and the storage.bin and a bunch of other useful files. So I'll just show you how to do that. So it's just ordinary arming of the vehicle. So the users had an issue, and then they rearm. They go for another flight, and or just arm it on the bench. So I arm it, and when I arm it, it then, as per usual, it writes a log file. But this log file is going to have a copy of the crash dump in the log file. All right, and you'll actually see a little message that'll pop up. You'll see it says logging sys crash dump.bin. For the crash dump.bin especially, we actually pop a message on the console so you know that it is actually logging a crash dump. The idea is to give the operator to know that this log file that they're, actually contains a crash dump from a previous problem. All right, so we've now got, I'm going to disarm again. And so it's now disarmed. That's just an alias, disarm force. And so let's log list. And we see log number 132, log download 132. And we'll see the little progress thing up here in MAVProxy, which shows the percentage. We are through downloading the log, 40%. Nearly there, 60%. 80, 90, and there you go. We've now finished downloading that log. All right, so we've now got log 132.bin. Right, so there's our log file. Now I'm going to load that log in MAVExplorer. Okay, so in MAVExplorer, we have a new command called the file command, right? So if I run file, then what it's doing is it lists all of the files in the log. And this is something that I was discussing earlier with Michael about adding support for this in Mission Planner. I think it'd be very nice to be able to extract these files. So basically our onboard log file, the bin files you have on the SD card, or they would also be on the companion computer if you were doing log streaming to your companion computer, contains a lot of the key data that you would normally get live. So if you're a company that supports your users and your user has an issue and they send you a flight log, you should look in it and see whether there's information in these files that can help you diagnose their issue. So for example, we could see whether they were running out of memory, right? We could go file sysmemory.txt. This is a copy of the @sys/memory.txt from when they armed. And we can see all the different memory regions on this particular board. So it's an H7, which means it's got 6 different memory regions, right? Not just a single memory region like on the old, most of our older boards, or 2 on something like an F427. So it's got these 6 memory regions, and we can see how much is free on each memory region, what is the largest one we could allocate on each region, and these type flags say whether the memory region is DMA capable or fast memory, these sort of flags. So this gives us all that information about what was going on with their memory at the time they armed. All right, we can go and grab, for example, their UARTs. Now, this gives us detailed information about what was happening at with their UARTs at the time they armed. You can see, for example, which UARTs are active. We can see that I was on USB, and so I had lots of transmission going on serial 0, which is a USB port, and lots of receiving going on those as well. So you can see that that's highly active, but these ports, for example, you can see that I wasn't using UART serial 4, serial 5, serial 6. It gives you both the serial number and the UART number. The little stars tell you whether it was using DMA. So we can see that this particular one, serial 1, has DMA available for receive, but not for transmit. And this one has DMA available for both transmit and receive. Really useful when diagnosing speed issues, packet loss, talking to companion computers. You can go and look at the time you armed whether you had DMA available on each of these channels. Let's have a look at our timers. All right, so we have information about the timers we're using and what frequency they're running at and what mode they're running in. We can see that we've got DShot 600 running on that particular timer. We can see the clock that was coming into it. This is the sort of information, for example, if Andy was helping you debug a DShot issue, you could give him the timers file and he would then immediately know exactly how he's setting up all the clocking, etc., for that DShot. Really, really useful information. All right, what are some of the other ones I want to look at? Are the threads? Yes, so let's have a look at the threads. Okay, so this shows all the different threads running in RGPilot. The RGPilot is very much a multi-threaded flight controller. And we can see the main thread, what its priority was, the address of where its stack was, which is useful when you're diagnosing with a backtrace. How much stack total it had and how much stack was available. That's the stack free and the total stack available to that thread. So you can see whether any of the threads had a low amount of stack, was running low. And you can also see what the priority was of all the various threads. We can see, for example, that this had a special ADIS 1647, which is for that fancy IMU, and it's running at a very high priority. And there's no particular stack issues that are showing up in these particular ones. All right, so we can see that scripting was running. Okay, so we can, of course, download our storage file. So I can go file that and let's call it e.bin. So I can go and download the storage file out of the log file. So that example I gave a minute ago where you wanted to transfer the storage into a simulator or potentially into another flight controller, if we made that writable, you can download that out of a log file, which is very, very powerful. So you can get that from your users and then try to reproduce, get exactly the same mission, the same rally points, etc. Absolutely identical storage as to what you had on the real vehicle, even though you don't have direct access to the real vehicle. We can, of course, get the crash dump. So I can go and download the crashdump.bin and have that as cd2.bin. So now we've downloaded that crash dump file, which has the same one. So I can now, let's go and copy that CD2 into here, and then I will be able to go and get a backtrace from this crash dump that came out of a log file this time instead of downloaded with FTP. And there it is. So we can now get a backtrace from a log file that a user has sent us, which is very, very powerful as far as, finding the cause of an issue. All right, now you also got all your Lua scripts. So we can go and I've got a ship landing Lua script on this particular one. I can have a look at that Lua script just by going file in the name of the Lua script. And there's the exact Lua script that I had running on the vehicle at the time it armed. And so I can tell exactly if I get a bug in a Lua script, I can go and look at the line number. You can also specify the name of file to download into rather than just displaying on a terminal. So if you go like that, then it downloads the Lua script as a file locally rather than just displaying it on a terminal. The default is if you don't specify the second file name that it just displays it on the terminal. All right, so you get the idea. We've got our storage memory. You do actually get the full HWDEF in case they've modified that. So you can have a look at exactly what they had. It has the comments removed, but you have the complete HWDEF for the boards. You know exactly what they were running, which is, again, very, very powerful if you're not exactly sure what was running or they're using the custom build server, for example. This would show all of the modifications they'd made in the custom build server, which would show up as lines of extra defines at the end of the hwdef.dat. All right, any questions about that at all?
What about missions and rally points?
The storage.bin has that. So you can get that out of the storage.bin and then start up CITL. We could separately dump those, but it's not really necessary because you've got the whole storage bin. That just makes things a little bit simpler. But yes, we could separate that out and have, you know, mission.txt, etc. But it would just add flash space as a feature, and it doesn't. I actually find it more useful to take that storage.bin, copy it to EEPROM, just fire up CITL, and then you can view the waypoints in whatever ground station you feel like, rather than just having them in a particular text format, because the text formats don't necessarily bit for bit replicate exactly what was on the system, whereas it does bit for bit replicate it by using the storage.bin. All right, any other questions at all?
I was just thinking about automating this, or building this into scripting tools. Is there a way to extract the files using MAVLog dump or something else that's not interactive like this?
Yes, I think, have I already done that? Let's see, MAV files. I thought I added a MAV file decode. I've got a MAV FTP decode. I could certainly make that available as a separate Python script. I didn't think it was too bad firing up MAV Explorer, but yes, we could have this as a PyMavLink tool. It's a very simple piece of code. If I bring up mavproxy and command file, so the code to extract it, this is the complete set of code for extracting all of the files from a log. It's just a few lines of Python. It's terribly simple because we made the file format very, very simple. So we could easily extract that out as a separate little script, which, for example, extracts all of the files out and just shoves them into the current directory or maybe into a subdirectory. So yes, it is a very, very simple thing to do because it's a extremely simple file format that's used. The only complexity in here is handling duplicates. Occasionally, if you armed twice, for example, you actually get every file twice. And so it's going through and handling those ones. And it's also reporting on gaps, because if you've somehow lost a message and you've got a gap, it tells you you've had a gap in that particular file. So any more questions about the files in logs?
I guess we don't have this ability in Mission Planner, right? I know
not yet, although I wouldn't be surprised if Michael is typing the code as we speak. Nice. We did discuss it this morning on the sort of the pre-call discussions, and it would be, I think, pretty easy to add in Mission Planner. So Michael, have you thought about this?
Michael?
Not sure Michael's online at the moment or has microphone on, but
there's a button in Mission Planner, to extract a whole bunch of other things, missions and parameters, et cetera. It goes through, parses it, pulls out those bits, and makes them available in separate files. And it would be nice if those were, that's right.
We do have Mav Explorer for Windows, of course, so you can fire it up. I'm sorry, was that Michael?
Into it.
He's looking into it. Yeah. It's something we could potentially do it as a plugin as well to Mission Planner. I've been meaning to learn how to write plugins for Mission Planner. I haven't yet written my first plugin, but I think it would be quite a nice little plugin to do that.
And sorry, I know I've asked this question before, but it is possible to stop the Lua script from being included in the log file, right?
I think we might have added an option for that. We certainly discussed that at the time because
because one of the nice things, I mean, obviously not for me personally. Everything I do is open, but some people want to have their Lewis scripts remain private, and of course you could just your log, and that would be fine. But if you wanted to,
but there it is there. So it is in there. So the SCR debug opts, if you set bit 2, which is value 4. So if you set SCR debug to 4, it would suppress the logging of the Lewis scripts. It shouldn't really be saying data flash, it should be saying to log file. But yes, it stops the logging of that. Yes, we should probably make sure we test that and just make sure before we release the final 4.2. But yeah, the intention was to be able to have a way to turn that off, to default it on, because I think most people would want it on, but have a way to turn it off in case it's important.
What if arming fails? That's often more the type of logs I get sent. Do you still get all this stuff on a failed arming? Like
at the moment, it won't log all these things with a log disarmed, which is the other obvious way to do it, just to set log disarmed to 1 and then get the log. At the moment, it doesn't. That's something that I've listed as a bug in my 4.2 bugs lists for plain, and that I was intending to discuss with Peter the way we could fix that. It's just the way it hooks at the moment. It hooks into the arming step, because what you can do is just do a forced arm. You can force arm the vehicle. You could even have the safety on when you force arm it, and so it doesn't actually spin anything. But yes, that is a lack at the moment.
Arm a real vehicle.
We could also have a MAVLink command to do this, to trigger it, or to force this to happen. But of course, if you can also just download it using the FTP interface in Mission Planner and download all of these files directly yourself, because Mission Planner already got a nice FTP interface.
Yeah, I guess you could have a MAVLink. I'm about to try to arm MAVLink command, something like that, or a start logging MAVLink command.
Yeah, I think we could have MAVLink commands, to open log and write all these things out right now, please, sort of thing. We could.
If I'm thinking right, then if you have a failed arming, then we should in fact log these things, because you've gone through the arming step, and we have a little hook thingy in there where we'll log for 15 seconds or something on a failed arming. But I can certainly see why setting log disarm to 0 wouldn't.
It doesn't work. It's just a matter of knowing how we fix that. What is the best way to fix that, and whether it should log them again. If you do have log disarm, should it log it again when you arm? I think it probably should, because you really the data at the time you arm is more useful than the data at boot, because all your DMA and UARTs and things and what's being used is more useful because your system's only just started.
Yep.
So I think we should probably double log it. Yeah. Okay. All right. So so that's probably enough on those files in logs. So continuing down our diagnostics demos, stack logging. Okay. So I've got this same little log file. Log file here and log132.bin, and this one's a nice simple feature. We can just do, we've got, if you tab, you see all the things you can graph in Mav Explorer. One of them is this stack log message, and the simplest way to get it is just to dump stack, and that will dump all of the stack messages. And so there they are, and I'll just make it a bit wider so it's a bit easier to read. That's probably better. And so what we can see now is it cycles. It cycles every 10th of a second. It writes out one stack message, and then it cycles around between all the different tasks. And you can see here that it's logging actually task number 255 there. That's the interrupt stack. And so that's the critical one. If you run out of interrupt stack, that's bad. You will end up getting a very, very nasty fault. So you've got to make sure they're stack free. So for each of the tasks here, we have the total amount of stack available for that task and how much is free, plus the name of the task. The ISR is the interrupt service handler. So here's our main arducopter process in this case. So it's got 7168 bytes of stack, and we've got 4.4K free. Our idle task, we've got 144 bytes free, and this UART receive. So we have a thread per UART on the transmit side. So this UART2, that's our transmit thread for each of these UARTs, and then we've got a single thread for all the receive of all the different UARTs, and we can see how much free space there is. So this is useful just if you think that they might be getting issues with running out of stack in a thread. For example, if they ArduPilot, if you get below 64 bytes of stack available in a thread, it will report an internal error of stack overflow. Now, it isn't actually overflowed yet, it's just getting close to it, but it reports it as a stack overflow error. So if you get one of those stack overflow errors, the problem is you don't really know which thread it is that's had the problem, and you don't know what triggered it to use all that stack. So these stack messages in your log file are what give you that extra information. So that allows you to see the history of the stack. You can see, earlier on in the flight, what happened to the amount of stack used on each one. You can then work out, at what stage of the flight, at what you were doing, mission upload or starting auto or whatever, at what stage of the flight the stack for that particular thread became low. And it also makes it very, very easy to see which threads are running low on stack. So this is what we reach for when we do little patches that might adjust up or down the amount of stack space that a particular thread has. This stack logging gives us the information that allows us to know, to know whether that's needed. So any questions about that at all? All right, so we'll move on. And so this next one. So this next one, I'm going to need help from the audience. So Josh, are you available to provide assistance?
It should be already streaming.
Excellent. All right.
Been streaming for an hour.
Great. So what this is going to demonstrate is CAN over MAVLink. And this is, we've had, and I'm also demonstrating forwarding of MAVLink. So Josh has Mission Planner attached to a flight controller. It's a cube orange, I think, Josh, is that right?
Yep, one cube orange.
Yep, and he's got 2 CAN buses enabled on that cube orange, and he's got some devices on one CAN bus and other devices on the other CAN bus. And what he's done is he's used this little nice interface here. So I'll just go full screen here. There's this, under the advanced setup, you've got this MAVLink mirror button. And that MAVLink mirror button walks you through the process of mirroring all the MAVLink that's coming into Mission Planner across to another address on the internet. Now, I deliberately have a public IP address on my home server, and that allows me to have a fixed address that is used. But you can use dynamic addresses as well, as long as you know what the address is. So he's set it up to forward to my address. So he's coming from the East Coast of the United States, forwarding MAVLink from that cube orange to my computer here. Okay, so what I'm going to do then is I should have, it's a little bit hard for me to see because the way, no, okay, I've just start up again. I'll make sure I don't have any MAV proxies running in the background, and I'm going to, so if he's forwarding it to 15.550, I use 15.550 usually rather than default to 14.550. That's just because I'm often using 14.550 internally in my network. So I make 15.550 be what comes in remotely from other users. And I'm going to, what I'm going to do is start up MAV proxy, and it's going to accept MAVLink in on UDP 15.550, and then it's going to show me the console, and then it's going to forward it out back to my own computer. And you will understand why in just a second. So here I am, and I am now connected to Josh's Cube Orange over there in on the east coast of the US, and I can show his parameters, etc. So I've downloaded all of his parameters, and let's have a look at all his CAN parameters, and you can see that he's got both CAN ports enabled, and he's running the drone CAN protocol on both of those devices. All right, so that's all well and good. This has been available for ages, being able to do CAN forwarding, and I could now forward that on to Mission Planner, or I could have received it directly in Mission Planner. So this is a very, very useful way of being able to diagnose errors with users' computers and help them with their setup. So I often connect in this way, and then I share screen with them, and when I'm adjusting parameters, I'm explaining what I'm doing. We're going to go one step further. I'm going to start up the Drone CAN GUI tool. All right, so I'm starting that up, and you notice that I had forwarded MAVLink out from this MAV proxy out to 127.001.14.550. So I'm going to connect the Drone CAN GUI tool to MAVCAN 14.550. And what that's going to do is have the Drone CAN GUI tool receiving CAN packets over MAVLink. And so I'll start that up. And now I'll enable the local node ID. And so there we have it. We are now seeing all of the CAN devices. We're managing the CAN devices on a Cube Orange on the East Coast of the United States from Australia. And so I can go and have a look at his airspeed sensor, for example, and I can fetch all his parameters, right? And check that he's got the right parameters on his airspeed sensor. It's a little slow, you can see, I can make it faster by clicking this low bandwidth button. Now, what that does is, I'll actually show you what that does if I run up the bus monitor. So here I'm going to have a look at all of the packets. This is now getting every CAN packet that's going on in his CAN bus being relayed to me here in Australia. So I can see all of his packets and exactly what's happening. You'll notice there's only about 16 packets per second, right, happening here. It's sort of 16 to 18. This number up here, the third number is the frames per second, CAN frames per second. I'm going to undo the low bandwidth tick box, which is up here. Right, so I'm now going high bandwidth. And now I'm getting hundreds of packets per second being forwarded over the internet. So this only works when you've got a decent, internet link. Not really fast. It's only tens of kilobytes to 100 kilobytes a second sort of level. It's not massive amount of bandwidth. But I'll just pause that now and show exactly what we've got. For example, here's his raw airspeed data. So we can see exactly what is happening on his CAN airspeed sensor. I can see the magnetic field state because he's got a compass on this bus, right? And I can see a GPS. So he hasn't got a GPS fix. He's probably indoors. And so it's showing, the exact state of what's happening with his GPS. So we can basically look in a great deal of detail what is happening on his CAN bus remotely. So the way this is useful is you're on the phone to your user, ask them to forward MAVLink to you, you fire up the Drone CAN GUI tool, and you can walk through issues that are happening on the CAN bus remotely. The low bandwidth button is there to cope with, you notice when I press low bandwidth, what happens with low bandwidth is at the ArduPilot side, in other words, inside that Cube Orange, it's setting a flag to say to only forward messages related to parameters and status and firmware update and a couple of other ancillary messages, right? So just the messages needed to be able to look at the parameters of a node and to be able to get the node status and uptime and that sort of thing. And that reduces the bandwidth requirements enormously. In fact, I've successfully used this with an old slow, SIK radio. Things like this sort of radio, you can actually get diagnostics on your CAN devices in flight over a really low bandwidth radio like that if you use that low bandwidth option. All right, so next thing that's very powerful about this is I can change which bus I'm looking at. Now, those of you who use the GUI tool with the 4.1 version will know that you have to set a parameter to map it onto a USB port. And the parameter says which CAN bus you're mapping. And if you want to change which CAN bus you're mapping, you've got to change the parameter and then reboot. With this CAN over MAVLink, you just change the bus number here. And what you'll find is the set of devices. We can see we've got, there's a here GPS on the bus, and we can now attach to that here GPS and pull its parameters. So there's the here GPS control, see exactly what's set on that device. And we can then change back to the first bus, and it immediately takes effect. We've now got all of the devices in our first bus. So we can change between buses instantly to see exactly what's happening on both of their CAN buses remotely. Now, I'm sure some of you are wondering, can you update firmwares? And indeed you can. So it takes a few minutes, but I updated the firmware on Josh's Maytech airspeed sensor remotely from Australia yesterday. So I could do it again now if people are interested in watching it, but it does take a few minutes. It's slower than a usual update. And it only works if you've got a recent bootloader on the device, because the original CAN bootloader we wrote for AP-PRIV has quite a short timeout for the round trip time for talking to the client that's sending it a firmware. And so it constantly times out when you're on the other side of the planet, just because of the speed of light and network delays, etc. But the latest version of the bootloader has a longer timeout in it, and it works quite well. It flashes, for the yesterday when I was checking with Josh, it was flashing at about 2 kilobytes a second. So a 200 kilobyte file would take about 100 seconds, which is a bit longer than it would normally take locally, but still quite acceptable. If you're flashing it over a low bandwidth link like a radio like that, it can be done. I have updated firmwares over a radio like this onto a CAN device. You can even do it in flight. You could actually update the firmware on each of your CAN devices in flight if you wanted to. Anyone who's got an octa-quad copter could be the first one to land with different firmware version on each of their ESCs than they took off by upgrading one at a time in flight, relying on the failover. That would be possible. But I'm not sure whether anyone's ever going to actually try that, but it'd be an interesting possibility. So you can actually update firmware over this, and particularly useful if you do the low bandwidth, so it stops all of the other messages coming through. So just the firmware update is using your bandwidth rather than consuming it with all of the sensor data. All right, so any questions about that at all? No? Okay. So when we're talking about the cloud stuff later, one of the things I'd really like to see is with some of the cloud control, that particularly what the talk from Hefny later about his cloud control stuff, being able to forward MAVLink in that cloud control system, so that when you're controlling a fleet of aircraft via a cloud-based system, you'll be able to forward MAVLink to devices like this and actually inspect CAN buses and update and change firmwares remotely. Via these cloud control systems. And I think that'd be something be really nice to have for a future version. Okay, so that's enough about the CAN forwarding. And so let's go back to the slides.
Oh, Tridge?
Yep, Tom?
That's Tom Pittenger. There's always a thing on that GUI tool that I've always wanted to use, but never could quite figure it out. Since you had it up there, I thought I'd ask you.
Sure.
The filter option, like if I want to look at just one ID or one packet on.
Yeah. Okay. So why don't we have a look at? I'll go full bandwidth, full rather than low bandwidth, and we'll bring up the bus monitor from Josh's one. All right. And say, for example, I'm only interested in the fix 2. Then I can just go fix 2 like that. It takes a substring of the packet, and now I'm only seeing the fix 2 packets here. Is that what you meant?
Yes. Okay. Can you do it by just by device, maybe? Is that
like the source ID? Or I haven't tried doing it by source ID.
Yes.
So that's something that's probably is quite useful. to be able to say a particular device. I just use it in the simplest possible way, which is put in a substring. I didn't write this feature.
You can add another filter, an additional filter, and just type 125.
Right. Okay.
I forget how I think it's
You
that button.
don't say source 125 or nothing like that?
No, it doesn't work like that.
Yeah. All right.
Wherever the additional filter button is, you do that.
Yeah, there's. All right. So this might be for a future tutorial rather than sort of exploring it at the moment. But I just do it with that simple way often. You can also, of course, graph. And you can, for those who haven't seen it, there's been a few other features added. You've got control in your ESC panel now for sending the safety off and sending arming things so for testing ESCs. And of course, we've got the plotter. So I could, for example, for those who haven't seen it before, I'll go and do a plot of, so for example, the number of satellites that that you're getting over there, which is probably not very many. So sats used, and I can pick a color for that plot. And so this will now do a little graph, and it's fairly boring, I'm afraid. You need more satellites over there. So you can now, plot field. So we could plot, it's probably more useful to be able to plot something like your magnetic field. So if I do, let's see, what about equipment, magnetic field strength, and magnetic field in Gauss. And so this is now got the 3 values of your magnetic field. So it's a vector. And so if you rotate that device over there now, Josh, then we will.
Yeah. I am, so it should be.
Yep, it is moving about. So this is now plotting the raw values coming in on the bus, on CAN bus. And so again, this is quite useful when you're doing diagnostics. You can see exactly what's happening on the bus. So this is coming all the way from east coast of the US to here, looking at magnetic field strengths.
I found the subscriber being the most useful for driver development.
Right. Okay. All right. So good stuff. I will move on from that now. So let's go back to the slides. And so this is now a little bit about what I would like to see at the system level for 4.3. As people should have already heard, we've gone to a new 6-month release cycle. And so 4.3.0 should be in beta in July of this year. And 4.3.0 final should be out around October of this year. So we've got that's our new 6-month cycle from what we used to be a roughly 12-month cycle, and so we're now halved that, and we're trying to get releases out a bit more quickly. So these are my top features that I would like to see at the system level. CAN-FD, with all the node capability stuff, definitely. So that's, I think, really important to start getting that rolled out. The new ShibiOS release that I've mentioned, the better QSPI support. Some Ethernet work. Tom and Sid have already started work on support for Ethernet. I'd really like to see Ethernet to be a supported feature for 4.3 if we can. I'd really like to be able to update firmwares from microSD. And this is particularly important. We have a large fleet of vehicles. Imagine you've got a drone light show with 1,000 vehicles, and you might like to update the firmware on all 1,000 vehicles. Going around with a USB cable to each of them is really painful. So being able to upload the new firmware to the SD card using MAVFTP, and then getting it when the next reboots, you send a reboot command and it sees the file on the SD card and flashes the firmware. I think that would be very powerful. It would also be extremely useful on vehicles where the flight controller is deeply embedded in the vehicle and the USB isn't readily available. I think it would be very, very useful to be able to update the firmware via off the micro SD card. And that's something that I've started prototyping.
If you need any more motivation for that, I try to update the firmware from the companion computer, but on some vehicles, you can't reboot without powering down the companion computer. So being able to update from the card would be huge for those too.
Yeah, I think it'll be a very useful capability. It's only going to be possible on boards that have got enough flash space in the bootloader. So you're not going to be able to do this, for example, on a Q Black because it's a 16K bootloader sector and that's full. We've only got a few bytes free. But on, for example, an H7 base board or an F7 base boards, I think it'll work. It'll be very easy. We can just make it a standard feature. So I'd expect that future releases, I'm hoping that in 4.3, this will be a standard feature to be able to update your firmware from the SD card. Multi-session FTP, as we make more and more use of the MAVLink FTP protocol, at the moment, there's only one FTP session that can happen at a time. So if you've got multiple ground stations or the ground station trying to do a mission and a parameter and a sys file all at once, then it just doesn't work. What happens was when you open a new session, it cancels the old one. And the protocol itself supports multi-session. It's just our server-side implementation inside ArduPilot doesn't at the moment. It kills off the old session when you start a new one. So we need to fix that and support that multi-session to be able to take better advantage of the MAVLink FTP. I'm thinking of adding, we've got an independent watchdog at the moment, what's called the IWDG, which is where we catch, really bad things going on in the flight controller. I'm thinking of adding a windowed watchdog as well. The advantage of the windowed watchdog, which is another type of watchdog hardware built into all of the STM32s, is the windowed watchdog would allow us to have a fault handler for when our main watchdog is just about to fire. And that would allow us to, for example, to log that crash dump for an arbitrary watchdog, even all zeros watchdogs, timer lockups, those types of things, the ones where we don't currently get a fault, which means we don't get the crash dump. If we had a windowed watchdog in there that gave us an interrupt when we're just about to get the watchdog, then that interrupt could do the dumping of all of the information. And so that's something that I'm hoping to get in for 4.3. I think we should consider removing or disabling EFK2 for 4.3, just because the flash space savings, and whether we just disable it, whether we have it in the code but not built by default. We already have it disabled by default at the moment. We've done that, since 4.1. The EKF3 has been our default state estimator. But I think to save the flash space, we should consider whether we're going to not have it built in on most of our flight controllers, or maybe all. And so if you really wanted EKF2, you would have to enable it in the custom build server, or we could go as far as just removing it completely, which would mean we wouldn't save us the maintenance burden. So we'd like to hear feedback from partners that might still be running EKF2 and why you're running EKF2. Is there some compelling reason for keeping it around? And if nobody can provide a good reason for us to keep it around, then we'll probably remove it and save the flash space for other features instead. So any comments on that before this opportunity to stand up for EKF2 and why it might be important?
I'll just admit that we're still using it, but for no reason except inertia.
Right, okay.
So if we're feeling really good that EK3 works as well and better, then
we're very confident EK3 at this stage. So I think we should consider removing it. So that'll probably be a dev call topic in the coming weeks. All right, finally, Henry asked me to remind everyone to keep the development docs up to date and the user docs up to date. And that link there takes you to the latest issues of things that need to be documented, and a lot of them have got my name against them. This is just a reminder that our documentation is really important for the good user experience, and so this is why I've got all the developers on the call. Yeah, Henry?
Actually, that's the wrong issues list.
Oh no, wrong one. Darn it, I thought I got this right.
4.2 is the one that needs work. This is the stuff that's already been released.
Okay, that's this one.
And this is all the stuff that is undocumented. It's not documented, nobody will be able to use it. And
right, okay.
So
All right, we've got, at least it's a lower proportion that is against my name, but still quite a few. Yes, there's a fair bit more documentation we need to get in there.
And again,
all right,
I'm more than willing to work on any of it, but I need some bullets to explain it to me
to get started.
On that. So,
all right, okay, thanks, Henry. All right, so that is it as far as my systems update talk. Sorry it droned on for so long, but I hope that was useful. So any final questions before we move on?
Tridge, there's a question you might want to answer in the chat.
Okay, let me see if I can.
From the Zoom chat.
Okay, there you go. All right, that's in the chat. How does the EKF outsource params handle EKF3? All right, so that's really a Randy question, as you did that work. Randy, do you want to answer that?
Yeah, so there's 3 banks now. In EKF3, it's better than EKF2. In EKF2, you could really just have one, one sensor. With EKF3, you can actually switch between the sensors in flight. So there's a wiki page. I think it's called something like GPS, non-GPS transitions, and it goes through the parameters. But in any case, the short answer is EK3 source pause Z. So EK3 source 1 pause Z is how you would change the main sensor used for the altitude estimation.
That's this parameter there that says which sensor it's going to use for the Z position. So that's the vertical position for the first bank of available sensors. All right. So any other questions?
How do you get those strings to define what the parameters are? That's fancy.
The new version of MAVProxy does that. It has you have to do param download once, or when you want to update. So you do a param download, it downloads that, and so when you go param show, then it actually labels all of them to show what it's set to. You can also do param help. Param help EK3 source 1, pos Z, and that explains what the different values are. But yes, it now displays as a comment whenever you set or show parameters what the current setting is. It also decodes bit masks. So if I do param set, I don't know, arming check to 7, then when I show that, that's showing it as all parameter and compass. So it decodes both bit masks and values when you're displaying them in MAVProxy.
Fancy. Thank you.
No worries. All right, any more questions?
I feel like that download needs to happen once automatically at some point.
Yeah, the problem is that often people use MAVProxy in an embedded environment, a companion computer. It may not have internet, and it could clag things up. So that's why I didn't. But yes, MAVProxy is full of these little sort of hidden gems like that, and you learn them by coming along to talks like this. But yes, it might be, we could perhaps display a warning, if it hasn't have it, or if it's really out of date, suggestion, download your parameters. Or the other obvious one would be to add it into the menu here, parameter download docs or something like that. That would be very easy to do, to add that into that menu. That might make it a little more discoverable. I expect a patch from you shortly, Tom.
Sure thing.
Why is it not just in the MAVProxy distribution? There's too many configurations, or?
We could bundle it potentially. Yeah, that would be possible to bundle that in. We'd have to download it at the time we build MAVProxy, download the latest docs, and then embed them in as a default set. That would be something we could do. Yeah. All right. So we're running low on questions, so we might move on. So I'll stop sharing, and so now let's have a look at our schedule and what we're up to. And
the schedule has Randy next.
Has Randy next. Okay, now what was the timing on that schedule?
I think he was supposed to start 45 minutes ago.
Well, no. So Randy is supposed to start at. Oh, really? Did I go for? How long did I go for?
Yeah, I'm afraid so.
Oh my God. Oh wow. Way. Sorry, I completely listened. My apologies. Okay.
Sorry.
Well, Randy, shall we have a break of a few minutes, or should we jump straight into Randy's talk? Sorry, I thought I was actually running short, but not long. So, all right. Randy, do you want to jump straight in, or do you want to have a break first?
Whatever. What do people feel like? Do people want a couple minutes?
I'm good to go. I don't know about the rest of them.
I'm good to go.